Every framework and library seems like magic before you fully dissect it. Maybe you don't need to import half a megabyte of code when you can hand implement the one feature you want. Let's break down APIs and inspect the building blocks rather than the skyscraper it turns into. And speaking of animated introductions, let's take a look at Tweening. This is From Scratch, Episode 2, Tweening. Now, unlike the previous video, I think I can explain this without diving first into code. You see, tweening refers to the process of creating the frames of animation in between two key poses. You might say that we'd like a circle to be animated from point A to point B. It should take 500 milliseconds to make that journey. There are many different ways for it to make its way over. It can, of course, teleport, or just teleport. It can stagger. It can have a linear move. And of course, things that are a bit smoother, like quadratic in and out. It's a bit glitchy here, but this is just for recording, as a recording artifact. Now, of course, a circle is an arbitrary shape. We can actually animate really anything. We can animate a progress bar. Let's do a linear one. Put this over here. We can tween the size of a square. We can tween a number. We can make it go up or down. So tweening just really needs a start and a destination. Now, how might we implement this in code? Well, since animation is just really a series of frames, our first attempt might be to take the start position and keep adding some number to it until it reaches the end position. We can do, let's say, 1. We can do 2, or maybe even 4. Now, this, of course, is arbitrary, and we're in a bit of a love-hate relationship with arbitrary these days. It can also be a bit more clever and add acceleration to our velocity. So over here, it looks like a bit more of a smooth movement going on. Now, either approach might work fine in a vacuum, but in practice, we normally need to control for time. With our current approach, we might be able to tweak the speed, but we can't define a duration. There's no way to configure our animation to last for exactly something like 500 milliseconds. Over here, we get kind of close, but not exactly. We can go a bit up or down, but we're never going to get exactly over there. Oh, that was too high. Oh, that was too low. Oh, we're too high again. In fact, given a starting point and an ending point, there's no way to input exactly how fast it should go. If we say 200% of its normal speed, then what is its normal speed? Do we go by integers? What if the start and end positions or values are both decimals? If we're running on a machine with a faster or slower frame rate, our animation's time is suddenly much different. Like over here, let's limit it to 60 FPS. That's weird. You'll notice that the previous animation went much quicker. That's because I used request animation frame, which tries to go off my monitor's native frame rate. In this case, that's 144 Hz for the monitor I'm recording this on, and 75 Hz for my second monitor. Meaning, the speed of the animation will actually change depending on what monitor is being used. In its current state, it's just not a very effective way to tween values. What we want is a value as a function of time. Although they appear very different, we can think of both our values and time as percentages, since they both have a destination. For any given percentage of time, we can return a percentage of value. The current time lasting at maximum 2,500 milliseconds, or 2.5 seconds, we can have an appropriate value. Now, of course, time is linear, so we can expect this thing to move linearly. If we just map our percentages one onto the other, that for any given percentage of time, return the exact same percentage of value, we're going to get a linear movement, which doesn't give us a whole lot of flexibility. Although, we can have other functions. Now, these functions, by virtue of being functions, are completely stateless. We don't need to know about the previous value, just what the current value is. And over here with the teleport, we see only when our current time is the end do we get a full position of our end value. With stagger, we can see how our position moves in response to the current time. With quadratic in, we can see that our time and value do not map exactly one-to-one, but the position slowly catches up towards the end. With quadratic out, we have the exact same effect, but in the reverse direction. Quadratic in and out, we have the same effect in both directions. There we go. And this is sort of what tweening is. That's how we want to implement it. We need to create a function that for any given percentage of time returns to us a percentage of value. And this could be the exact same percentage for something like linear movement. It can be a staggered percentage for something like stagger. And of course, the other ones get a bit more complicated. And with that sort of introduction, let's see if we can dive into code. Now, this presentation here, I'll try to make it available online. I'm not sure what the link will be. I'll see if I can put it in the description. Maybe it'll be just on GitHub. We'll see when I upload. All right, now let's get our project going. So this is the project we're going to be working with, where we're going to be using and explaining how the code works. We have two files over here. We can see to the left, we have index.html and index.js. Index.html just has some basic styles. We have the size. This isn't really used. Just some random stuff over here. We don't really even need this border. This SVG fills the entire width and height of our page. Inside of it is a circle. I could just have used a div with a border radius of 50%, but I figured this would be kind of nice. This isn't used either. Struck with, spelled that wrong. It's currently positioned in the middle of our screen at 50%, 50% with a radius of 20, and it is filled with black. All right. Now, our JavaScript isn't very complicated right now. We're getting the SVG and the circle. We're adding an event listener to the SVG, which is essentially the same thing as adding an event listener to the body. And with this event listener, where we click on a part of the page, the circle will move its position to that point. See? Whenever we click, we get the client X and client Y, and we use that to set the pixel value of the CX and CY, which is the X and Y position of our circle. No tweening really happening here. So we want to have movement. But for our project, what we're trying to do is have the ball be tweened to the value we set it to. So whenever we click on the page, we want the ball to move there smoothly. That's our sort of goal right now. Right? So let's move on to version 2, and I'll show you what I changed for this one. Again, using the same sort of Git system I used from last video. This time I'm going to use VS Code to transition instead of, typing into the console. This is a bit easier, a bit smoother. We haven't changed anything in the HTML for our second version. We've changed a bit over here with the index, a bit over here with the tween.js file, which didn't actually exist beforehand. And I'll sort of click over here and I'll show you what I did. So this is actually, from a video, the essence of tweening. We've already sort of done it. It's over. Video ending. But of course we're not done exactly yet. I want to show how I did this and what changes I made to get this sort of result. So the first thing I did was I stored the X and Y value on the top level scope for our ball over here as a value. So I got the bounding client rect, which gives me an object that defines some properties of our circle, like its width and height, but importantly, its X and Y position. So I store that in my values because in our HTML, we set it to percentages and we want to use pixel values. So to start, X and Y are pixel values. Whenever we click on the page, we take the X and Y values, we store it in start X, start Y, we take the click value, and we store it in destination X and destination Y. Now, we store these values over here because we're actually going to change these during the course of our animation. So we can't really rely on them while we're animating. We don't want to rely on these values. So once we set these values, we get the current start time, which is performance.now. This is similar to doing date.now. There's no real good reason why I decided to do performance.now. If you're wondering what that returns, let me just make this a bit bigger. Performance.now returns a timestamp since basically how long the page has been open. This is in milliseconds with everything after the decimal being in, I believe, nanoseconds. Again, you could have just used date.now. I have a utility function called loop4. Now, this is something I made because I don't want to confuse the code showing, all the nitty gritty. I'll show that in a second, but just so you can see the page, this is really all we're trying to focus on. This utility function takes a callback, let's say, and it calls that function for an undetermined amount of time every frame. So this actually uses request animation frames. This could run the function 144 times a second in my case, or 75 times a second in your case, or 30 times a second. It doesn't matter, but it stops looping after this duration is ended. So after 250 milliseconds, it stops looping. How many times it loops? That's not for us to really decide. Now every frame, it gives us the current time. Now the current time, again, is using the same sort of metric as performance.now, which is why I had my start time also use performance.now. And I subtract the current time by the start time. So it's the number over here. This gets the difference, meaning how long it's been since we started. And I divide that by the duration. Let me just move that over there. There we go. Now this gets us over here the percentage of how far along we are into our duration. So if we stop after 50 milliseconds, this will be 50 divided by 250. Whatever number that is, we can find out in console right now. That would be a third of the way there. So 33%. Now with our percentage, what we do is we call another utility function called apply percentage. This isn't especially complicated. I'm going to go over it in a second. But all I do is I get that percentage of distance in between our start x and destination x. So we have two values, the start and stop, and I get the value in between them according to this percentage. So whatever value is 33% in between the start x and destination x is what I return from this function. Again, not especially complicated, but that's what this does. I get the x value, and then I set it. Over here, I can do the same thing for the y value, and I set it over here. And that's our entire tweening. So we're essentially done with tweening. And I want to get this point across in all of my from scratch videos, that the core concept of these libraries is usually very, very, very simple. It's when you want to make things easier for your end user, when users don't have to control for the loop for function, for the percentage thing, when you want to handle that on the library side. That's when things start to get a bit more complicated. So let's go into our utility functions and see what they actually do. So for apply percentage, again, not especially difficult. We take our max value and we subtract it by the min, and we multiply the percentage times new max. So let's say our minimum, and I'm going to use console just to explain this math over here. Let's say we're trying to go from 25 to 50, right? So in order to get 50% of the distance between 25 and 50, we have to first subtract 50 by 25, which is the actual distance. This is what we call the delta. The delta between our two values, the difference, the absolute difference between 25 and 50 is 25. And this is what we're trying to apply the percentage to. So if our percentage is 50%, we do 0.5 times 25, and we get 12.5. Now we have to add 12.5 back onto our minimum to get actually how far. So 25 plus 12.5, that's 37.5. That is the actual value. This is the value that is 50% in between 25 and 50. And that's all this function does. It's not especially complicated, but it's easier to, put that in a utility function than code it ourselves. The loop for function, a bit more complicated, not especially, but more to do with APIs. We get the start time with performance.now, the same thing we did beforehand. We get the stop time by adding the duration to the start time. Again, that's just how time works. With over here, we create a function called animate, and we loop this using request animation frame. If we're not familiar with request animation frame, it's a function provided to us by the browsers that run a function sort of corresponding to your monitor's refresh rate. So 144 hertz monitor, you'll get 144 frames per second. This essentially tries to make animations run smoothly. Now again, because it runs a certain amount of times, per second that we don't know the number of, that we can't really control for, you shouldn't be using request animation frame if you're trying to you rely on the loop to have a consistent frame rate. And we don't really need to, because we're going by the time percentages. So you pass the current time, which is actually provided to us by the browser. We don't have to provide this ourselves using performance.now every 2 seconds. And we check if current time is over stop time, return. What this does is it doesn't call request animation frame, meaning it doesn't loop itself again. That's all it does. So loop for essentially provides duration. It stops after that duration is over, and it just calls that function each time request animation frame is called. All right, nothing too crazy or complicated. Now let's try adding the tweening. Let's try adding the cool movements, the values. So now we have a very linear tween, which again isn't very pretty to look at. It moves, we can click on the screen, it tweens to our value, it lasts exactly 250 milliseconds, but this isn't necessarily exactly what we want. Let's go to version 3. Now, this is going to be a bit more complicated. You can see I've added the tween functions over here. In index, I haven't done anything too crazy. Let's go back and forth just so I can show you what I did. Let's go to version 2, and let's go back to version 3. You can see I added this. which is a drop-down menu over here. And I've added this, which takes the tween funct thing that we've defined in tween.js. And instead of, and the only change really made over here is instead of just taking this value as a percentage, we passed this percentage to the tween function, which returns to us another percentage. So the idea of tweening functions in general, and I've said this beforehand, I'll say it again, it's to transform a percentage. It takes a percentage as we've seen it and transforms it to another percentage. We're still dealing with percentages yet. It doesn't give us a new value. It takes one percentage and turns it into another one. Now, what kind of things do these do? Now, I actually have a link from a friend of mine. Let's see if you can actually look at these. And this is a it's a website on easings. I think this is actually kind of a really cool thing to look at. So with a linear movement, you'll see that for any given measure of time, we have the exact same measure as the output percentage, which ends up being a linear tween. Over here, we see they're sort of exactly on the same slope. So a linear tween would look like this. An ease like this, where you have an ease in, or we call this maybe a quadratic in-out in our area, will look like this, where the start is a bit smooth, the middle is a bit fast, and the end is a bit smooth. All right, we're still working with the domain of our time. There are many other kinds of tweens which we will not be discussing. These are really cool. The elastic in, elastic out, the bounce in, where you have a cool bouncing animation. Overshooting over here, overshoot out. So these are all really cool. The math behind these isn't super simple. Maybe in another video I'll go over them. But I'm not going to really touch the specific tweening functions. All you have to know is these are literal functions that for any given x value will output a y value, which is of course how functions work. For any given measure of time, they'll output a corresponding percentage of value. With elastic out, this actually goes above, so this can output more than 100%. It's still percentage, but it might output higher than 100%. Anyway, let's go over the basic tweens as we see them over here. So linear, this is any given percentage of time, returns the exact same percentage of time, which is just linear over here. It's sort of unnecessary to have this function, but this is a possible way to tween values linearly. Don't really do anything. Don't transform the percentage at all. Quadratic in says that for any given percentage of time, multiply that percentage of time by itself once, and that is that time squared. And what that gives us is a smooth transition in, but a much faster transition out. Again, you're going to have to trust me on this one. I don't really have diagrams to explain it over here. Cubic in does the same thing, but multiplies itself 2 times, so it's cubed. This is to the 4th power for quart in. Now let's look at them, how they work. Let's go to linear, let's go to quad in. You'll see that it starts off slow and then it gets very fast at the end. Starts off slow, gets very fast. Let's go to cubic in, starts off slow, gets even faster, even faster, even faster. And then, of course, quart in, and we're just going up. We're just going higher and higher. So yeah, you can just do to the 30th power and have it go super fast. The math here is pretty simple. With stagger, I think this is a cool way to transform values. This isn't very practical. I don't think people really do this regularly, the stagger animation. But all I'm doing over here is I'm saying math.floor t times 10 divided by 10. So what we're doing is we're multiplying it by a number, we're removing the decimals, and then we're dividing it by that same number. So what we do is we end up getting 10 steps. If we change it to stagger, this gives us 10 steps. Now you can't really see it on the video because we're limiting the frame rate. Let's limit it to 3 steps. Go over here, 3 steps. Stagger. 1, 2, 3. See? 3 steps the entire time. That's the idea of stagger. Doesn't look very pretty, but maybe you want like a pixelated sort of movement. Let's just Control Z for that. So quad out. So the out animations are a bit more complicated, but the idea here is to sort of reverse the animation. Now again, the mathematics is not the main point of this video. I'm not really going to go into it too much, but the idea of quadratic out is you take the time and you get the reverse of it. It's a really clever way how to flip a sort of graph where you take 2, and again, our time is going to be 0 to 1, right? We know t is going to be 0 to 1 because that's the only possible percentage of time that we can get back in. And we're expecting this to be between 0 and 1. So 2 times t will return a value between 1 and 2. And we multiply our time by that value, which gives us, so 2 minus this will get us a value between, sorry. And so t times that will get us sort of a flipped version of the quadratic in. It's weird, again, I'm not going to go into the math. This video is not on the math itself, just the idea of programming. Quadratic in-out is one of the more complicated ones, and for any in-out, what you're going to see usually is a lot of if statements. And especially with things like elastic in-out, there's a lot of if statements over here. You're combining a lot of, you're merging a lot of different sort of functions together. So over here, if we're between this, return this value. If we're greater than that, return this value. Math is not the point here, but quadratic in-out ends up working that way over here. So again, this is the entirety of our tweening, not library, but our tweening code example. If we wanted to transform this into a library, we can abstract some parts away. The loop for, this is a bit more of an imperative way, I think, to write code. I would prefer to do this in a more declarative way, where we just have a looping function and it does things for us. But essentially, there's 2 points, there's 2 aspects of tweening. And this is sort of what most libraries miss. And it's, I think, one of the more pain points of tweening libraries. And so for our tutorial, to make this as simple as possible, what I've done is I've created 2 main functions. There's a tweening function, which provides to us a function to tween with. And there's a runner, a function which actually runs the animation. And I'll show you what it looks like. Let's go to the 4th and final one. And our code looks a bit cleaner over here. Now, I've changed a few things over here in the area. Let's go through this one by one. So for tween, this is, I guess, the core part of our library, and it's absolutely tiny, if you can see how small this is. But this is a function which returns a function. So we could have written this a bit differently, but to not confuse everybody, I've written it like this. You take in a tweening function, and again, these are the same functions from over here. These are the tween functions. You probably get a better name for this. Not sure what to call it, though. Maybe a transformer. We have a start value and a destination value. This can be anything. I think for my purposes, the start has to be less than destination. I should probably change it, though. I haven't tested it out. I'm assuming it actually doesn't have to. Anyway, with percentage, we're taking our tween function and we're transforming the current time percentage to a value percentage. Right? Same old, same old. That's what these do. You give it a time percentage, it gives you a value percentage. Then we apply that percentage to the start and destination. We take this value percentage and we actually get a value out of it by applying it to the start and end. The runner takes in the function that this returns. It takes in a callback, meaning what function do you want to run every time based on this value? And it takes in a duration, how long to run this tweening for. And then it loops for that duration using the loop for command we made earlier. It takes the callback and passes it over here with the time percentage that we calculate using this over here. And transforms the tween over here and it returns it back to the function over here. In practice, it looks like this. We get the tween x by calling tween with some values, and we call runner over here. Now, what I've also done to runner and to loop for is I've added a should stop boolean so that we can stop this loop by calling the function that this function returns. And I'm just returning that over here. So for index.js, we can call stop tweens to stop our value. So whenever we want to sort of run a new tween, because it's possible that I want to tween before I've stopped the current tween, right? So over here, I don't want to wait for the whole tween to stop. I want to be able to stop it while it's moving and use its current value for my next tween. So I set x equals value on each function, and then my start equals x, my destination is e.clientx. And we can see how our code looks a lot simpler here. We can see how our functions work. We can see why they're so simple, why the concept is so important. And really, that's the gist of this video. That's the idea. I've gotten to this similar time as I did my last video, 25-ish minutes instead of 30 minutes. I'll see if I can leave links in the description. But that is the essence of tweening. That's how you can make it. It's not nearly as complicated as it looks. Probably the more complex parts are the actual easing functions, which you can just steal from online. A lot of people didn't really invent these. We sort of use functions that someone else has made. But, you know, doing merge curves and stretch X, this is a bit more of an interesting way to do things, which I might go into in a later video, I might not. We'll see if there's any really want for it. Thank you for watching. I don't really know how to end this video.